The last section of this chapter is taking the derivatives of exponential functions and logarithms. So let's just jump right in and let's get down to business. And again, just like the last section, if you really want to see what's going on behind, you can talk to me or take a look at the book. It will give you all the background information. But for our purposes, we're just going to go ahead and throw this out there. So the derivative with respect to x of e to the x, that's the main exponential we'll be dealing with, is e to the x. It's the only derivative, it's the only function whose has itself as its derivative. So you're definitely going to want to remember that. And then his buddy, the derivative of the natural log, is 1 over x. And you're going to want to remember that too. So those are both extremely important. And in fact, this actually brings up a very good point that you may have been asking yourself as you were taking derivatives. You never were able to take a derivative and get x to the negative 1 as your answer. If you notice, in this case, we get x to the negative 1. So as you were taking derivatives, you know, we know, like, oh, if I have x to the 3 and we take his derivative, or x to the 2 or x to the 1, when we took the derivative, we got an x squared. Here we got an x. Here we got a 1. And then let's say I said x to the 0, right? And then let's say x to the negative 1. Well, x to the 0 is a constant. So his derivative is 0. And then x to the negative 1 is negative x to the negative 2. Well, I skipped 1 in here. I skipped 1 over x. What happened? Well, now we know what happened. The function you take the derivative of to get 1 over x is the natural log of x. Okay, so memorize those, know those, and get ready to use them because they're going to pop up all over the place. And along with this comes a process known as logarithmic differentiation. And by the time we're done with this section, you should be able to take the derivative of just about anything. So logarithmic differentiation goes like this. If I have a function with a variable in the exponent, and I'm going to take a very, very simple example. I'm going to say a to the x, where a is a constant. So this would be like y equals 2 to the x, or y equals 5 to the x. And in fact, what you're going to see in a minute, or y equals e to the x. So basically, here's the idea. I can't do calculus to that function because the variable is in the exponent. So what I'm going to do is take the log of both sides. Now, what you just got done seeing is that this is the log of choice, because the derivative of the natural log is 1 over x. So you're obviously going to say, well, wait, what if it was log? Okay, well, if it is log log, then you're going to do algebra, not calculus, to find the answer. Because let's say someone says to you, well, I've got a function log base some random base b of x. You take the derivative of that. All you have to do is the change of base formula like you did back in Algebra 2. You say, oh, I know that I am allowed to take basically the log of x, this piece, divided by the log of b with any base I choose. Okay, well, I choose base e. And when you do that, b is just a constant. B is some kind of number. So this is actually 1 over log b times the log of x. 1 over log b is a coefficient, just like any other number. This is like 1 over 3 or something. Who cares what it is? We don't know what the number is, but it doesn't really matter. It's a constant. So can you take the derivative of this now? Yeah, because this is just a constant that will come along for the ride. So if they give you log, do a change of base to make it an ln, and then employ this rule that the derivative of the natural log of x is 1 over x. So in this case, the derivative of y in the blue over here would be 1 over log b times the derivative of this is 1 over x. Okay, anyway, back to logarithmic differentiation. I am going to take the natural log of both sides of the equation. So this is the game we play. We take the natural log of both sides of the equation because that allows us to bring the exponent down onto the main line of operation there. So we get log y equals x times log a. Again, the natural log of a here, remember, a was just a constant. That's how I set this problem up. This will just be a number. So this is like a coefficient for this x, just like if I had the number 7 sitting there. If I said x times 7, okay, just keep that in mind as we go through this problem. If the base here was not a constant, that's okay. It's no big deal. So if this were some sort of function sitting here, no big deal. We would just have to use the product rule because we would have the product of two functions. In this case, I don't need to because this is a constant. So what I'm going to do now is take and implicitly differentiate both sides of this equation. So given the thing we just circled a moment ago up here, the derivative of log of the stuff is 1 over the stuff. That's what we're going to do. So in this case, the derivative of log y with respect to x, remember, so we're actually going to do implicit differentiation here, is 1 over y, that's the derivative of log y, times dy dx. So there's our implicit differentiation. And we take the derivative of x log a, like I said a minute ago, that's like saying x times 7 or 7x. The derivative of 7x is 7. So the derivative of log a times x is log a. That's just a constant. Well, I've almost got this solved for dy dx, so we're almost done. So dy dx in this case, I'm going to have to multiply both sides by y. It would be y log a. And here's the thing. I told you guys before that if the function you're given is implicitly defined, then it's okay to give a derivative that has the x's and y's all jumbled up. But if you look back at this original function, y equals a to the x, that's an explicitly defined function. Y is in terms of x's only. So I really should not give you an answer in terms of y. So we're going to do a substitution because, lucky for us, we know what y is. It's written right up here. Y is a to the x. So a to the x log a. So I just demonstrated the process of logarithmic differentiation, but by doing so, I also showed you that if you have something like y equals 2 to the x, the derivative of that is 2 to the x log 2. And that's always going to be the case. So you can feel free to use this as a rule, as if I had just handed it to you. Obviously, logarithmic differentiation has many, many more uses. Anytime I have a variable in the exponent position, I have to use logarithmic differentiation. But you can use this particular example as a rule if you want to do other problems. Actually, we can see now that at least math is consistent, and I'm not saying this is a proof that, in fact I'm saying it's not a proof that the derivative with respect to x of e to the x is e to the x, but at least you can see that we are consistent, because if I did say, hey, let's take the derivative of that, you would say, okay, it's e to the x log e. Oh, of course we know the log of e is 1, so we wouldn't need that at all. And that's logarithmic differentiation and how we take the derivative of logs and exponentials.